Welcome to Study Loop.
So this problem has us looking at an orbital transfer for a spaceship that's around the Earth and then wants to go to Mars. So originally it's in orbit with Earth, and then it's going to transfer into Mars's orbit. So after kind of looking at the diagram for a while, which can be helpful, we can realize the situation is basically like this. So in green here we have the Earth, which is in a circular orbit around the sun, and then Mars in blue here with its much larger circular orbit. And so the satellites or the spaceship is originally with Earth, and then it wants to transfer into this longer elliptical orbital, and then it rides that over and then gets into Mars's orbit. So then it re-enters a circular orbit with Mars and then can land on Mars. So we're looking then at basically this large elliptical orbit. And so the sun is at a focus of that, and then the two endpoints here are the distance from the sun to the Earth and then from the sun to Mars. So first we're asked just to kind of describe like what this whole process will be. So we've kind of done that a little bit. So originally we are just in orbit with Earth going around the sun, but then we want to enter this elliptical orbit, which is going to be more energetic. So we need to increase our kinetic energy somehow. So probably a common thought then would be that, oh, we need to increase our speed. So you fire the thrusters in the direction that the rocket's traveling, and that'll increase the speed. But actually what you want to do is fire the thrusters in the opposite direction of motion. So this is kind of counterintuitive, but this causes the ship to initially slow down, but then it'll move into a slightly lower orbit. And lower orbits are going to have a faster velocity with them. They need to be moving faster to stay in orbit. So doing this actually causes the speed of the ship to increase, and then it's able to shift from its original circular orbit into this longer, more energetic elliptical orbit. So it fires thrusters against the motion to enter this long orbit. And then once again, it needs to now increase its energy when it's reaching the Mars orbit. So this big orbit has more energy again, and so it fires its thrusters against the motion again when it reaches here, and then it's able to dip a little bit, but then speed up in doing so, and then enter this big orbit. So then returning from Mars to Earth, it does just the exact opposite. So this time instead it fires the thrusters with the direction of motion. So that's kind of part A, not really anything specific we have to write, just kind of the description that we gave. So part B then asks us to find how long the one-way trip from Mars will take. So basically then, if we're moving from here to here, that's half of this total orbit, and so it should just be half of whatever this period is. So for an elliptical orbit, we know our period from Kepler's law should be pi a to the 3/2 over the square root of gm, which in this case would be mass of the sun since it's still in orbit around the sun. And so a here would be the semi-major axis. So that would be half of this long part of the ellipse. And so we can see then that that is just going to be 1/2 of the distance from the sun to Earth plus the distance from the sun to Mars. So just half of this distance plus that distance will give us A. And so when we plug that in, we get 2.24 times 10 to the 7th seconds, which comes out to be about 259 days. So then part C is kind of interesting. So that says to reach Mars, we must time our launch so that Mars will be at the right spot. And so what must the angle be between the Sun-Mars line and the Sun-Earth line? So they're talking about these two lines we've just drawn. So right now the angle between these is 0 or 180 degrees, depending on how you want to measure it. So we'd probably say that's 180 degrees. So when do we actually want to launch it? Well, this 259 days that it'll take to get there, if we look up what the length of Mars's period is around the sun, we can see that that is about 0.378 times the period of Mars, so times a Mars year. And so during this time, we know that the spaceship needs to kind of travel through an angle of 180 degrees. So it has to do half of this orbital period, or this orbital length. There's no way around that. But if Mars is going to have moved 0.378 of its way around its journey, we can see that that will come out to be so 0.378 times 360 degrees in its full revolution would tell us that it's traveled about 135.9 degrees during that time. So that means we actually want it to start 135.9 degrees away from this endpoint. So really we want it to be like here or so. And so if we launch when it's originally here, by the time the spaceship would be able to get there, then Mars will have traveled all the way around here. Oh, and I guess really Mars is more out here in its orbit. So Mars is here. So then it'll have traveled over here to the right spot. And so if the spaceship's going 180 degrees, if Mars will have gone 135.9, that means that this angle theta here needs to just be the difference between those. So 180 minus 135.9. which should be 44.1 degrees. So we actually launch when Mars is only 44.1 degrees between its line and the sun, Earth's line and the sun. And then by the time the spaceship gets to the right point, then Mars has traveled all the way around in this orbit and made it to where it needs to be.